Hello there, my name is t.croisfelt.batista and I'm going to present you our work sent to the ENCIT2020 conference. This work was developed under supervision of the Professor Júlio César Passos and Edson Bazzo, and it was carried out at the Federal University of Santa Catarina in Brazil. About the presentation agenda, I'm going to introduce you the context and the goal of this work. After this, we are going to take a look on the methods deployed here, and then I'm going to explain the achieved results. In the end, I'm going to summarize the conclusions of this work. To introduce you the context, we need to know that geothermal oil wells are very similar of oil and gas wells. They are even drilled by the same companies around the world. This may highlight the opportunity to reuse the abandoned wells in the oil and gas sector in new geothermal power plants to generate heat or even clean electricity. In this work, we studied this possibility in the Brazilian oil field. About our methods, we started selecting 4 abandoned oil wells. They are located in Brazilian states of Mato Grosso, Paraná, Rio Grande do Norte and Santa Catarina. And we are going to refer to them by the abbreviation of the state where they are respectively placed. We recovered real built and rock types data from the logging profile to build our simulation models. To recover heat from the lithosphere, we considered a closed cycle and deployed the double pipe heat exchange concept. In this system, we placed the production tube in the center of the wellbore. Then cold water, is injected in the annular portion of the well. And while it goes down, it recovers natural geothermal heat from the rocks. Then this heated water is extracted from the bottom roll through the inner pipe, the production tube. Moreover, to develop the calculus in this model, we considered some simplification hypotheses about the liquid water, the stream, the built-in structure. Also, we coupled this system to an organic Rankine cycle to simulate the conversion of the extracted heat into electricity. We created a numerical model for this system using the finite volume method. We considered the problem axisymmetric with rocks represented here. The reinjected water after going through the power cycle in the annular portion here. The upstream of the heated water here in pink. It was not possible to estimate the heat flux to the atmosphere due to the complexity of the soil surface and windy conditions. So we considered the top surface with a constant temperature equal to the annual average for each location of the wells. Also, we deployed a bottom domain offset to avoid edge effects in the heat stream profile. Moreover, we deployed empiric formulations to estimate the friction factor and the convective heat transfer in the water streams, and we sized the domain and mesh as shown. Now, covering the results, there is a particular situation about the model validation. We did not find any real experiment or test to run our model and compare results, but we made some sanity checks. They were about the energy balancing in the steady state. We also checked if the thermally affected zones reached the domain boundaries. They should not touch the domain boundaries. Moreover, the calculated geothermal heat flux should be flat along the bottom surface domain and in accordance with values expected by the literature. Also, we evaluated the Reynolds and Prandtl numbers along the entire domain. They might be in accordance to the accepted ranges for deployment of the empirical formulations. One of the most expected output of this study is the heat power potential of these geothermal wells. We have here their transient profile along the simulated life cycle. And we can see a decay along the years. For the Mato Grosso case, for example, it starts around 400 kilowatts and it decays to around 2050, trending to the steady state here. This decay shows that lithosphere works as a thermal capacitor. In other words, the rate of geothermal heat supplied from the ground does not equate with the extracted heat power, and this phenomenon is associated with the need to drill new wells in traditional geothermal power plants from time to time. Moreover, the deepest well, this one in blue, has more area to exchange heat with the ground and the higher extracted heat rate. But some work shows that actually geothermal gradient is more important than depth, because deeper wells need more pump power to operate and they deliver less net electricity. About the temperature profile, just for information, here we have the natural rock temperature as function of depth, and here the annular flow temperature from injection down to the bottom hole temperature. Initially, we can see a decrease of the downstream water temperature. It goes like that until some point, and then only from this depth it starts to recover heat from the rocks. This happens because injection temperature is much higher than the soil surface temperature, and so the ambient temperature. There is some constraints in the power cycle related to the pinch point temperature that makes it impossible to re-inject water at a lower temperature, which results in an unused exergy that's dissipated to the top layers of the soil and then to the atmosphere. This behavior happens in all case studies. Here we have the unidimensional heat rate profile. It presents some abrupt profile changes due to main discretization, which changes in the well diameter and the rock properties. This heat rate profile also changes a bit from 1 to 3 years of life cycle. Most important, it highlights the effects of the high injection water temperature and how it results in a huge loss in the process of heat extraction from the rocks. There is this positive heat going to the top layers of the soil, causing a decay in temperature that we saw in the previous slide. These losses reach values around 70 and 80 kilowatts, and only after depths around 3 kilometers, this lost energy is recovered, from where the water stream starts to have positive balance in energy. And again, this behavior happens in all the case studies. About the inner flow, the water upstream, it also transfers some heat to the annular flow, implying a decay in temperature from the bottom to the head of the well, which is limited by the thermal insulation of the pipe. Moreover, the bottom hole temperature is the highest temperature of the water in this cycle. Another finding is that the water viscosity cannot be neglected. It varies significantly along the strings. This affects the calculations of the Reynolds number and therefore the estimated for the friction factor, the number of Nusselt, and the heat transfer coefficient. All the hydrodynamic and thermal problems are dependent on the variations in viscosity. Also, due to the water viscosity, the friction along the water strings converts the fluid potential energy into heat, resulting in a pressure drop between the water inlet and the outlet points at the wellhead, and about the pressure of the water and the lithosphere, they can reach values up to 500 bars at the bottom of the well. So, to conclude, we can say that geothermal heat extraction from abandoned oil wells is technically feasible. For the present concept and case studies, heat power can range from 157 to 411 kilowatts, and the hot source temperature can be between 89 and 104 degrees Celsius. Other important finding from this study covers the heat losses, and further studies are required to minimize the heat escape to the top layers of the soil. Also, to better insulate the inner flow and to reduce water viscosity effects. We would like to thank the Brazilian Agency of Petroleum and Natural Gas and Biofuels for granting access to data of the wellbores. We also thank the Coordination for the Improvement of Higher Education Personnel for funding the scholarship of the master's students enrolled in this project. And thank you all for watching. Bye.